In a previous video, I discussed the frequentist interpretation of probability and that it applied to experiments that can be independently repeated under identical conditions. On the other hand, the Bayesian interpretation treats probability as a degree of belief, which I motivated using an example about placing a bet when the assumption of repeated identical experiments did not apply. The degree of belief can be then adjusted in light of new evidence, and in this video I will provide an example. So here's Bayes' theorem. Given events A and B, the probability of A given B equals to the probability of B given A times the probability of A divided by the probability of B. And here is the theorem once we apply the law of total probability to the denominator. Now, we've been calling it Bayes' theorem. However, the form we all recognize for this theorem is actually due to the work of Pierre-Simon Laplace, one of the greatest scientists of all time. He independently proved and extended Bayes' results in 1774, apparently unaware of Bayes' work. Furthermore, Laplace is credited with the Bayesian interpretation of probability. In fact, there is wide agreement that the theorem should have been named after Laplace, but that's not how history works. Laplace was the first to think of Bayes' theorem as a way to assess the credibility of a hypothesis using available evidence, like this. The probability of a hypothesis is true given evidence equals to the probability of the evidence given the hypothesis is true times the probability the hypothesis is true divided by the probability of evidence. Those terms are known today as the prior probability, the likelihood, the marginal probability, and the posterior probability. Laplace further recognized that the marginal probability is a constant with respect to the event that the hypothesis is true, and so he deduced that the posterior probability is proportional to the likelihood times the prior. That is what Bayesian statistics is all about. So let's illustrate with an example how Bayes' theorem can be used to assess the credibility of a hypothesis given available evidence. Paul the Octopus became famous during the 2010 Football World Cup games. He made 8 predictions and they were all accurate. And a lot of people thought he was psychic. So was he psychic? Let's frame the question this way. What is the probability that Paul is psychic given the evidence? Here the hypothesis is Paul is psychic, and the evidence available is that he made a total of 8 predictions and they were all correct. Next, we will examine the frequentist and the Bayesian solutions, starting with the frequentist one. Remember, I'm interested in the hypothesis that Paul is psychic. However, the frequentist solution starts with the opposite hypothesis of interest, called the null hypothesis, or H0, that Paul is not psychic, then proceeds to verify H0. So the question being considered is not whether my hypothesis of interest is true, but rather whether the evidence is plausible given H0. Specifically, what's calculated is a probability called the p-value, which is the probability of obtaining a result like we have seen in the data, or more extreme, given H0 is true. H0 was that Paul was guessing, so there is a 50-50 chance that he'll get it right, which corresponds to a success probability of 1/2 for each one of his predictions. And this results in a p-value that is very small. Therefore, H0 is rejected in favor of the alternative hypothesis that Paul is psychic. Not only did I get a silly result, but the p-value did not answer my original question. What is the probability that Paul is psychic given the evidence? Instead, it sort of answered the inverse question. So let's use Bayes' theorem because it calculates directly the probability that I care about. The probability that Paul is psychic given the evidence is given by this expression. So I need to calculate the prior probability, the likelihood, and a couple of other terms. The Bayesian solution starts with the prior probability, which is our degree of belief that the hypothesis is true based on information external to the evidence or data. Specifically, what is the probability or degree of belief that Paul is psychic prior to observing any data? Different people will use different values here, but I'm going to say that there is a 1 in a million chance that he's psychic. Next, we need to calculate the likelihood, which is the probability of observing 8 correct predictions given the hypothesis is true. Well, if he has psychic powers, the probability of an accurate guess is 1. So let's calculate the posterior. The probability of the evidence given the hypothesis is false corresponds to the 50-50 chance that we calculated earlier. The probability that the hypothesis is false is 1 minus 1 in a million. So this is my posterior probability for the hypothesis that Paul is psychic. The evidence of 8 accurate predictions updated my prior probability that he's psychic from 1 in a million to a posterior probability of 26 in 100,000. However, that continues to be a very small probability and not enough for me to change my mind. And that is really why Bayes' theorem is special. It provides a coherent way to combine a prior belief with evidence in order to update that belief. But be careful what you believe in the absence of evidence. Suppose I'd specified a prior probability of 0 that Paul was psychic. Notice that the posterior will always come out 0, because in the numerator I multiply by the prior, so even if Paul made 1,000,000 accurate predictions, that won't change my mind. Analogously, if I had specified a prior probability of 1, that is, if I were absolutely certain Paul was psychic, then I would always get a posterior probability of 1. So again, I won't change my mind. And the moral of the story is to have a prior probability that allows you to learn from evidence, or you will be forever stuck in your prior belief. So as a rule, prior probabilities of 0 or 1 should be avoided, especially if you're open to trying green cheese made on the moon. This principle has a name. It's called the Cromwell rule. You should Google it.